Okay, I guess we're going to go ahead and get started here. We've got a pretty good turnout so far for a Monday morning. And does anybody have any questions about anything? Okay. So everybody should have seen the links I sent out for the YouTube videos. I'll try to do that every day. It's a whole lot easier than trying to send them out all at the end of the week. But as I generate the video, I can get the link and I'll go ahead and send the link to you. It just, last week, it seemed like it took a long time to get the videos to load. Maybe it'll be better this week, we'll see. Maybe everybody was trying to load videos at the same time. But I will have them loaded for lecture today and lab on Tuesday, I guess. We have our lab, the A11 lab is on Tuesday. So as soon as we get done with the class, I will have that video link posted for you. Any questions on anything? Now, I will say that we have lab this week. We'll finish up the second half of Unit 1, and then I will probably open up the test the following week on the 7th, and then let it run for 10 days. On the 7th, though, we're going to go ahead and start looking at bones, because the more time we can spend on bones, the better off we're going to be. I'll just tell you that. And those of you that have lab on Tuesday, you'll hear that same thing again, or Wednesday or Thursday. So let's see. Okay. So if you have questions on anything, don't be shy. Send me an email. A lot of people did last week, and that was fine. And I think I got everybody answered. So today we're going to start chapter 2. We're going to take a look at chemistry. And while chemistry is not everybody's favorite topic, it is something we have to address in A&P, more so than anything else about body chemistry, the changes in the human body of the chemical nature. We're not going to get into detailed general chemistry or organic chemistry or anything like that. We're going to understand the simple procedures that take place in our bodies. And you're going to see when we get into AP2 and we talk about body chemistry and fluid levels and electrolytes, which are the body's salts, that there is no faster way to kill your patient than to let those levels get messed up and then try to fix them. You know, it's not something our bodies like to see changing around. So body chemistry is a very important topic. I can't emphasize that enough, and you'll hear more about that in AP2. And then if you're going into nursing or any other healthcare, you're going to hear a lot about it in there. So, okay. So with no further ado, and what the do is anyway. So I'm going to go ahead and get into chemistry for us. And everybody should see the slide. It says the chapter 2, the chemical level of organization. Okay, this is working really well today. Okay, so to understand chemistry, we got to understand matter and energy. Matter is whatever things are that have mass, not just weight, but mass, you know, bulk, things like that. It takes up space. We can see matter. We can smell matter. Gases in the air are matter. We can water or any liquid is matter. We can feel it, we can see it, we can smell it. If we take the mass of matter and allow gravity to pull on it, we've got weight. So weight is nothing but the mass of an object being pulled on by gravity. Objects in space, up in the space station, for example, or in orbit, still have mass. May have no gravity, but they still have mass. And if the mass is large, it is still a large mass, whether there's weight or not. A person that weighs 200 pounds on Earth still has that mass in space. You just negate the force of gravity, but we don't lose the mass. We only lose the pull of gravity. So we lose the weight. So we say, and this is getting really off the topic, but then we say things are weightless. Now, matter can be in three possible states. It can be a solid, something with a defined shape, your laptop, your tablet, your computer, your notebook. They're all a solid matter. Us are solid. It has a definite shape. It has a definite volume. A liquid has a changeable shape. You can open up a 2-liter bottle of Coke, and the fluid, the volume inside there has a definite shape according to the shape of the bottle. And you can pour some of that into a cup. And now it's going to assume the shape of the cup. You can knock it over and it spills out and it assumes the shape, a flat on the countertop or on the floor. It assumes the shape of where it is. So it has a shape that changes. I mean, you swallow it. It changes its shape when we swallow it. It's no longer in the cup or in the bottle. It changes its shape. It has a definite volume. If you drink a liter of any fluid, it's still going to have the same volume. You drink a 2-liter bottle of Coke. I don't know why you drink a 2-liter bottle of Coke, but let's say you're really thirsty. So you drink a 2-liter bottle of Coke. It had the shape inside the bottle. It had the shape inside the cup. Maybe you just skipped the cup and went straight to the bottle. But now it's in your body. It's a different shape there, but it's still the same volume. Liquids have different shapes, but they have set volumes. Gases have the best or the worst of both worlds. They have a changeable volume and a changeable shape. You can compress a gas. You can take a gas and compress it, and it will liquefy. And if you compress it enough, it will freeze, and it will get into a smaller and smaller space. So the shape state changes and the volume changes by the state of the gas. If you take atmospheric air and compress it into a small space, it will have changed its volume and changed its shape. So gases are extremely flexible. They are still matter because they have mass and they take up space. All of the air in the room you're in right now could be collected and weighed. It would have mass, and it's taking up space. Fluids take up space. They have volume. They are matter. They have mass. Solids, of course. So everything, matter falls into the category of solids, liquids, and gases. And it's anything, whether we eat it or drink it or breathe it or smell it or taste it, all these things are matter. Now, the other part of chemistry deals with energy. Energy is the ability to do work. And work is essentially putting matter into motion. Every time we do something, every time we manipulate our environment, we are doing work. We are using energy to drive our car, our truck, to light a fire, to turn on our computer. We're using energy to turn on our computer. or our phones. Our phones are stored energy, and we do work. Believe it or not, that is work for the phone anyway, because we are putting matter into motion. Energy has no mass. You charge your phone, the phone weighs exactly the same as it did before it got charged. The energy doesn't have any mass. The energy doesn't take up any space. It's only the battery in your phone or your laptop or any device that you charge up is what is taking up the space. The device that you charge, the battery, is taking up space. It has mass, but the energy, the electricity, the stored energy doesn't have it. Your battery is no bigger or no heavier than it was before. So now, what we're seeing here is energy in action. We can't see the energy. We can see the consequences of the energy. The ball on the left strikes the other four. This is called Newton's cradle. And the ball on the left causes the ball on the right to move. We're transferring energy across there. And then we do the rebound action here. We are using energy to get something done. So we can, this is just a simple demonstration here of a transfer of energy. Do you see the energy? We don't see the energy. We see the consequences of the energy. If you light a match, you see the release of energy. You see the release of heat energy and light energy. But you didn't see the stored energy inside the match before it got lit. Let's go on now. Types of energy. Kinetic and potential. You've probably heard this before somewhere. Kinetic energy is energy in action. When our ball in Newton's cradle is moving, it's demonstrating kinetic energy. When the ball is in its rebound position before it starts moving to strike the other ball, it has stored energy. Let's go back. This ball in the end, when it's in its rebound position all the way up here, has gained energy. It has potential energy, which is now using as it moves forward and turning it into kinetic energy. We move kinetic energy and potential energy back and forth all the time. Potential energy is stored energy. When you charge your phone, you don't use all the energy that you put in there. When you charge it up to a full charge, you plug it in at night. In the morning, it says 100%. Now, you're not going to use 100% of the energy the very first time you check your mail or check anything else in the morning, or send a text or something like that. You're not going to use 100% of the energy. You're going to use some of it. Most of the energy in your phone is potential energy, stored energy. Once you use it, once you start using it, then it becomes kinetic energy because you're doing things. Even though we're not seeing anything move, you're still using energy. So that you're using what's known as energy in action, kinetic energy. So we have stored energy, and that's potential energy. And then kinetic is energy in action. If you eat something, if you get a cereal bar, for example, it says 130 calories or whatever in it. That is potential energy. I mean, that cereal bar is not doing anything. It's just laying there in the wrapper and says, hey, I got 130 calories. Well, that's great. It has 130 calories of potential energy, which then we can use when we break it down in our bodies. That's stored energy. It's sort of like a battery for us, except we can't renew the cereal bar. We can recharge the battery. Kinetic energy is when we do something with the stored energy. We do something, we manipulate our environment. So every time we contract a muscle, every time our muscles contract, we're using kinetic energy. Every time our heart beats, that's kinetic energy. Every time we breathe, that's kinetic energy. When we pump blood through our bodies and have a pulse, that's kinetic energy. Potential energy is what's in our fat cells and in our glycogen, stored as chemical energy, stored there, ready to go, ready to use, or even in the food that we're getting ready to eat. If you're eating an apple, a cereal bar, a donut, a banana, you know, a biscuit, an egg McMuffin, you know, whatever. The calories in the food that we eat all represent potential energy that we can use. And we switch back and forth from kinetic energy to potential energy all the time. The gasoline in your fuel tank, or gasoline or diesel, whatever fuel you have, whatever kind of vehicle you drive, when you fill it up, that's potential energy. When you burn it in the engine, that's kinetic energy. It's energy in action. You know, you store energy in your gas tank. You don't use it all, you know, you don't blow through the whole gas tank at one, you know, in 1 second. You trickle it out into your engine. So we take that stored energy and turn it into kinetic energy, and our vehicle goes. Now, this is an example, maybe it's good, maybe it's not, of energy in action. Let's see if I can get this thing to play for us. Here we go. Once again, no sound. Okay. Energy in action. Now this is one thing about energy is we don't create energy and we don't destroy energy. Energy is never destroyed. It is just transformed from one form to another. So here we see low potential energy in the bow. When the bow first starts out, you just pick up the bow and the arrow and notch it on the bow. That's potential energy. When you draw it back, that's kinetic energy. Releasing the energy, you actually are storing energy in the bowstring. Then you transfer that to the arrow flies through the air and strikes the target. Of course, anybody can hit a bullseye if you're standing 3 feet away from it. But so the potential energy from the bowstring here, that's stored energy right now, transferred to the arrow. The arrow goes through the air, it hits the target. That arrow actually warms up. And you could measure, because the arrow is going through air and it's going to have friction from the movement of air, you could actually measure a temperature increase when the arrow strikes the target. Now the energy comes from the food that we have eaten. Now, all the food that we eat, we break down to release the energy from that. We also get proteins and lipids in there too, but we convert the food chemistry into other types of molecules that allow us to release energy. So the energy we get in our bodies all comes from our food. It's all, we're converting potential energy into kinetic energy. So let's move on. If you ever go to Dollywood and you go on any of the rides there, maybe the Eagle or any of the other ones, it's actually an experiment every day in potential and kinetic energy. When you go up, when you're on the roller coaster, that first hill, you rise up in the first hill, and we're spending lots of energy to get you up to the top of that hill. When you are up here, you have a lot of energy has been put into the system. So at the top of the hill, you have a great deal of potential energy. You've stored all that energy getting up to the top of that first hill, that first rise in that roller coaster. And the steeper the rise, the longer the ride's going to be on the other side. If you like roller coasters or any rides like that, you know, the longer the ride up means the more powerful ride's going to be going down, because we have to, the amount of energy spent going up is going to get balanced by what comes down the other side. Notice how potential energy goes up when the ride goes up, and kinetic energy is released when the ride goes down. And if you did not discount the price of friction, it would be exactly balanced. Things that get shot into space, you know, we see, you ever watch SpaceX, you know, if the rocket's going up and they bring the first stage back and land right there back at Cape Canaveral, right on the pad. It's like dead on. It looks like something out of it actually looks like something out of a science fiction movie from the 1950s. But it works. But the amount of energy spent sending that rocket up is balanced by what is spent bringing it back. Because you'll notice it has to fire its engine when it comes back to negate the force pulling it down. Because the force that sends it up is going to be balanced by what's coming back down. So it has to balance itself out by firing its engine to land. So it, you know, why do spacecraft go through a re-entry phase when a spacecraft comes back from space? Re-entry phase is very hot. Well, because the friction through the air balances out the amount of energy spent to get it up there. Our universe, you'll hear me say this a lot, our universe has to stay balanced. Our universe has to stay balanced. Energy gain is going to get balanced by energy used. Types of energy? Well, we have chemical energy. In our bodies, we release chemical energy all the time from the foods that we eat. And a lot of that chemical energy is converted to electrical energy. We are electrical. We have a charge in our bodies of somewhere between -70 and -90 millivolts. That explains how our nerve impulses travel, because they are electrical. All of our nerve impulses are electrical, controlling our muscles. Our muscles move because they're stimulated from our nerves, and our nerves are sending electrical charges to our muscles, and our muscles do things because of that. And that allows us to have mechanical energy. We manipulate our environment. We move things. We pick things up. We pump blood. We breathe. We swallow. We churn food in our stomach. All this is mechanical energy. Radiant energy, we see things because light energy comes in through our eyeballs. So the sound wave, and not sound waves, but light waves, light rays, packets of light, strike our eyeballs and tell it, and we see things, and we can then convert that light energy into chemical energy, which is turned into electrical energy. So we send signals to our brain and say, hey, here's what we see. So we have, you know, we use this. We're exposed to radiant energy when we're outside in the sun. We're busy generating vitamin D in our skin because of it. So we use chemical energy, electrical energy, mechanical energy, and radiant energy. We use mechanical energy all the time to hear. Sound waves are pressure waves that come into our ears and cause vibrations, and that is mechanical energy. We're moving the little bones in our middle ear and sending signals to our inner ear, which then get converted to electrical energy. So this is all, you know, we use all these types of energy in our bodies. We convert all the time. We convert from one form to another. When you turn on your phone, you're converting the electrical energy in the battery to light energy, because you have a display in your phone. Sometimes you've got the flashlight feature on your phone. That is electrical to light. Or if you're going to consider the battery is chemical. Believe it or not, it's chemical going to electrical. Or the example here of turning on a light, you go from electrical to light right there. You skip the chemical aspect of it. The problem with energy conversions is every time we go from one form to another, we lose some of the energy as heat. We don't destroy energy. Energy is never destroyed. We don't make energy. We don't destroy energy. The amount of energy in the universe is a constant. We don't make it. We don't destroy it. We just use it. And we convert it from one form to another. And when we do that, as we convert from electrical to radiant, turning on a light bulb, for example. If you try, if you reach up and try and touch the light bulb, I don't know if you're unscrewing the light, if you turn on a light bulb and then unscrew it for some reason, the light bulb's hot. Light bulb gets hot because when you're converting from electrical to radiant energy, there's heat energy being given off. Now that heat energy is not destroyed. It just becomes unusable because the heat radiates out from the light bulb. When you drive your car or your truck, the energy, you have gasoline in your tank or diesel in your tank, and it goes into the engine. The engine burns that fuel, and that chemical energy is converted to mechanical energy. Well, in doing so, you generate friction as the cylinders of your engine are moving back and forth inside the engine, and you generate friction. Now and that means a lot of heat. Our engines generate a lot of heat, and we collect a lot of that heat by the cooling jacket of water that surrounds the engine. That's what the radiator's for. We all know that, but a lot of heat comes off of there. And so that heat is energy that is lost. We can't use it. It's there, it's giving off heat, but we don't use it. Our bodies are the same way. Our bodies, when we eat something, when we eat an apple, for example, the apple has, I don't know, I think 60 calories are in your average apple. Let's make it an above average apple. We'll make it 80 calories. So you have 80 calories in your apple. And how much of that 80 calories are we going to get to do something with? Well, it turns out about 60% of those calories are going to be lost. Oh, let me go back. I didn't mean to do that. 60% of those calories in our bodies are going to be lost as heat. Well, that gives us a constant body temperature. That's not such a bad thing for us. That keeps us at 98.6. The amount of heat that we give off from converting chemical energy in food to mechanical energy or electrical energy in our bodies is only 40% efficient. The rest of it comes off as heat, but that heat maintains our body temperature. You don't think that we generate a lot of heat. Get about 100 of your closest friends and put them in a small room and stand there with them and see how hot it gets pretty soon, because we radiate an awful lot of heat. And most of that heat becomes unusable. If you have a lot of people in a small space and they're radiating a lot of heat, what are you going to do with that heat? It's not a lot. It's going to radiate out. And the thing is that heat doesn't get destroyed. It just spreads out further and further and further into space. If we could find a way to capture it and use it for something else, that'd be great, but we usually don't. Okay, so the thing to remember is every time energy goes from one form to another, we lose some of it as heat. Friction gets in the way all the time. So every time we change forms, we're going to have a heat loss. It's not that it's destroyed, it's just it's converted And when it becomes heat, it just spreads out. Now, the basic parts of chemistry consist of atoms and elements. Matter is made up of elements. What's an element? Well, an element is the smallest version of a substance that retains all the properties of the substance. Well, that's a convoluted definition. You can't break an element down into something simpler like water. Water separates out into into hydrogen and oxygen. But hydrogen can't be separated into anything else, and neither can the oxygen. Gold is an element. Gold can't be broken down into something simpler than gold. Silver can't be broken down. Carbon can't be broken down. Carbon dioxide can be separated into carbon and oxygen. But you can't break the carbon down into something else, to something simpler than carbon. There's nothing simpler than an element. And it still has all the properties. The smallest part of an element still has all the properties of that element. In our bodies, the big four that make up most of our body are carbon, oxygen, hydrogen, and nitrogen. 96% of our body is carbon, oxygen, hydrogen, and nitrogen. Water makes up a big chunk of that. Water, we are about 70% water, and so oxygen and hydrogen there. Carbon, all of our carbohydrates, all of our lipids, all of our proteins are all have carbon involved there. Nitrogen is present in our amino acids, in our proteins, and in our DNA. We have another 9 elements that make up 3.9% of the body, and another 11 that make up the remaining 0.01%. So, but the big four are carbon, oxygen, hydrogen, and nitrogen. Now, the elements have been organized into a table called the periodic table of the elements. And there's about 114 different elements. I've highlighted the important ones here that are in the body. Hydrogen, carbon, nitrogen, and oxygen are the big four. But then we have sodium and magnesium and sulfur and fluorine. And then we have smaller and smaller amounts in here. The trace elements are in purple. The common elements in the body are in green. But the big four are hydrogen, carbon, nitrogen, and oxygen. And we can find them on this table called the periodic table. And if you take chemistry, I'm sure you'll learn all about the periodic table. For us, it's a convenient way of looking at these different substances. We can tell them apart from the table. Now, what are we seeing here? Well, we're seeing atoms. The periodic table of the element represents the atoms. It shows the atoms in each it shows the atoms of the element. All elements are made up of atoms. Atoms are the smallest particle of an element. It has those same properties of the element. An atom of oxygen has every property of oxygen. An atom of gold has every property of gold. It melts at the same temperature. It solidifies at the same temperature. It has the same structure. Just like oxygen. Oxygen, an oxygen atom will behave like oxygen does, because there's nothing smaller than an oxygen atom when dealing with oxygen itself. The atoms are all different. An atom of carbon is different from an atom of oxygen. An atom of hydrogen is different from an atom of nitrogen. They all have different properties. So the atoms are, when we're looking at the periodic table back here, we see this periodic table. What we're getting is we're getting information from each one of these letters on that particular type of atom. The information contained in this block with the C for carbon on the periodic table will give you the number of subatomic particles that belong to that atom. And it's the subatomic particles that give each atom its individual properties. How is a carbon atom different from an oxygen atom? Well, it has to do with the subatomic particles, the protons, the neutrons, and the electrons. Now, if you look at the periodic table, and if we were in a classroom, we have a big one that's like 8 feet across and 6 feet wide, or 6 feet deep, but it has every element known up through about 114. Most elements are naturally occurring. The last 10 or 12 that show up in the periodic table are artificially created. So when we look at the periodic table and we see a letter on there, or maybe 2 letters, that is an abbreviation for the element. Some are very simple. O is the symbol for oxygen. C is the symbol for carbon. Well, that's hard-hitting fact there, but O for oxygen, C for carbon, S for sulfur, H for hydrogen. That makes perfect sense. We throw you a little bit of curve here where we have names like Na for sodium. Na is the old Latin name for, abbreviation for natrium, which is the name for sodium. Kalium is the name for potassium. So if we go back and look at the periodic table, we can see on the far side, there's the K for potassium, and we see Na for sodium right above the K on the far left-hand side. Na for sodium makes no sense at all, except natrium is the Latin term for sodium, and kalium is the Latin term for potassium. Then we see Ca for calcium, Mg for magnesium, Li up here for lithium, carbon, nitrogen, oxygen, Ne for neon, He for helium. Some make perfect sense. Fe is iron, ferrium or ferrum, Latin term for iron. Some make sense, some don't. Cd, cadmium, Ag is silver. Au, wherever it is, there, Au is gold. Some make sense, some don't. But these are the abbreviations of the terms. Cu is copper up here. Copper, nickel, zinc, cobalt. Cr, chromium. As, I think that's arsenic. Kr is krypton, argon, xenon, radon down here. So, and here's one. Fm, I think, is fermium, named for Enrico Fermi, one of the early atomic scientists. So anyway, a lot of different abbreviations here. We're not going to need to know, a lot of that. Carbon, hydrogen, oxygen, nitrogen, sodium and potassium, chlorine. Those are the abbreviations we're going to use the most of. Hydrogen, oxygen, carbon, nitrogen, sodium, potassium, calcium. Those are the atoms and elements that we're going to need to know the most of. Every atom is made up of subatomic particles. We have protons, neutrons, and electrons. They're all the same. Every proton is exactly the same as every other proton. It doesn't matter what atoms it is in. The protons are the same. They all have a positive charge, and they all have what we call an arbitrary atomic mass unit. What that means is that protons weigh 1 atomic mass unit. Neutrons, the second subatomic particle, have no charge. They're neutral. They also have a weight of 1 atomic mass unit. Okay, so we have protons and neutrons. Most atoms are going to have neutrons. Not every atom is going to have a neutron. Some do, some don't. Every atom will have protons. Protons have positive charges. Electrons have negative charges. They have no weight. They're so small. They have essentially a 0 atomic mass. However, protons, despite their very tiny size, electrons, despite their tiny size, balance out the protons. The negative charge of a proton, the negative charge of an electron balances out the positive charge of a proton. And in our atoms, a stable atom, for every proton it has, will have a negative electron. The positive charges on a stable atom are always balanced by the negative charges. So if you have 3 protons, you will have 3 electrons. Protons and electrons balance each other out because the universe loves stability. Everything is designed in balance. Protons, neutrons, and electrons. And it is the combination of protons, neutrons, and electrons that determine the properties of each individual atom. Because each individual atom will have a different number of protons, neutrons, and electrons. For example, hydrogen has 1 proton. It has no neutrons. And since it has 1 proton, it has to have 1 electron. Proton has to have, if it has 1 proton, it has to have 1 electron. Helium has 2 protons. It also has 2 neutrons and 2 electrons. Has to have, it doesn't have, we have, the protons and electrons have to be balanced. There's no rule on the neutrons. We can have as many neutrons as we want in there because neutrons don't do anything except contribute to the weight of the atom. They don't affect the charge. But protons and electrons are going to have to be balanced. Lithium, for example, the third element on the table, has 3 protons. It has 3 protons. It has 3 electrons. It has to have 3 electrons, but it has 4 neutrons. The number of neutrons doesn't have to match at all on the number of protons and electrons. Protons and electrons have to match. A couple terms now: atomic number, mass number, isotopes, atomic weight. So what is the atomic number? Well, the atomic number is the number of protons in the nucleus of the atom. We're not going to worry about the subscript here, where it belongs. Atomic number. On a periodic table, the atomic number is a number usually above the symbol. So if we had lithium, we'd have a big 3 above that abbreviation for lithium. That's the atomic number. Number of protons, it's also the number of electrons. Now the mass number is a different number. It's written underneath the number on the periodic table. The mass number is the number of protons and neutrons together. That's the mass of that atom. Now lithium, remember, let me go back here. Lithium has 3 protons and 4 neutrons. So you add up the protons and neutrons for lithium, 3 protons and 4 neutrons, and that gives you 7. And so lithium would have a mass of 7. So on the periodic table, you would see a big 3 above the lithium symbol and a 7 below that. The 3 is the atomic number, the 7 is the mass number. And then you also have the atomic weight, which is usually the same as the mass number, because the atomic weight is the average of all the masses of all the isotopes. Ooh, what's an isotope? Well, an isotope is an atom with a variable number of neutrons. We'll get more into that in a second, but you've heard of carbon-14, right? Maybe carbon-14 dating, for example. Carbon-14 is based on a carbon atom with with a different number of neutrons. The normal carbon has an atomic weight of 12 or a mass number of 12. Carbon-14 has a mass number of 14, all because it has 2 extra neutrons. Anyway, I'll get more to that. So all we have to worry about are 2 things. 3 things if you consider the symbol. You know, if you have hydrogen, for example, you'll have a 1 above it, 1 proton, and you'll have a 1 below it. You know, 1 proton, you know, so its atomic number is 1 and its atomic weight is 1. Carbon has a 6 above it. It has 6 protons, also has 6 electrons. Its atomic weight, or its mass number, if you will, is 12. There's the other things we have to know. Atomic number and mass number. Atomic numbers in the top, mass numbers in the bottom. So the atomic number is 7. It has 7 protons. If it has 7 protons, it has to have 7 electrons. And the weight number underneath is the combined weight of protons and neutrons. No neutrons, that's fine. If there's no neutrons in the nucleus, then the atomic number is the same as the mass number. If there are neutrons, you just add the neutrons and the protons together. Atoms are neutral. Protons and electrons always balance. 6 protons equals 6 electrons. Carbon has 6 protons. An electrically neutral carbon atom has 6 protons and 6 electrons, evenly balanced. Protons and neutrons stay in the nucleus. That's the center of the atom, like a little solar system. Protons and neutrons are in the center of the atom, and surrounding the atom in orbit are the electrons. It's like the planets revolving around the sun. So we have protons and neutrons held together in the nucleus. Not the same as the nucleus inside a cell, but the concept's not too far off. Protons and neutrons together in the nucleus, electrons orbit around the nucleus, like the moon going around the Earth, or the planets going around the sun, for example. And there's a couple of ways of looking at how atoms are organized. There were two good models, the planetary model and the orbital model. The planetary model was very simple, and it worked, but it is, you know, if you're a chemist, it's not correct, because electrons don't spin around the atom's nucleus like the planetary model shows. The orbital model is a description that shows where the electrons are likely going to be, because these electrons are moving so fast. They're moving at the speed of light, which is 186,000 miles per second. You can't see electrons. They move so fast. if you could take a picture of an atom, you would probably just see a fuzzy ball around there because of the speed of the electrons. Because they're moving so rapidly, you can't tell exactly where they are. And that's fine. You know, frankly, we don't care. You know, what we're more concerned about is the fact that there are electrons in orbit around the nucleus, and the electrons are balanced by the protons. You know, in A and P, you know, we're not going to get excited about which model is used. We're more concerned about the fact that we know that there are protons and electrons in that atom. We're not going to get too excited about that either. So there's your planetary model on the left-hand side, and it shows helium. Helium has 2 protons in the nucleus, and it has 2 electrons. Doesn't show the protons, but they're really there. So we have the electrons are in orbit around the nucleus. Those orbits are fixed. Those are fixed distances apart. I mean, sort of like, you know, while the orbit of the moon around the Earth is a little variable, but, you know, but it's somewhere around 240 to 250,000 miles. It varies over time, but it doesn't vary a whole lot from 240 to 250,000 miles. The moon doesn't dip close to the Earth and then go back. It stays right around, you know, that's sort of a constant, somewhere around 240 to 250,000 miles. You know, the distance from the Earth to the sun is we've always been taught around 93 million miles, and it probably fluctuates a little bit, but, you know, a few 100,000 miles when you're 93 million miles away is background noise. The distances are fixed. So planetary model gives you a real good idea of what these electrons are doing. They're spinning in orbit around the nucleus, and they're spinning very, very fast. And that's what the planetary model can't show you. The electron, the other model, the electron cloud model, which, you know, is the other, you know, the orbital model. Planetary model shows you them stuck in position. The orbital model doesn't show this. The orbital model shows the cloud. We don't see the electrons. And here we see, yeah, there's helium, 2 protons right there, and a big fuzzy cloud around it, or like you see over in this illustration on the right-hand side. The electrons are moving so rapidly, we can't tell where they are. We know they're in orbit. We know they're moving around. We know that the orbit is a somewhat, you know, is, you know, on average, it's a fixed distance, just like the moon and the sun and the Earth, moon around the Earth and the Earth around the sun. It's generally the average of the fixed distance. It's 93 million miles Earth around the sun, 240,000 miles more or less for the moon around the Earth, and whatever the electrons are in their first orbit around the nucleus. We can't tell you exactly where they are at any given time because they're constantly moving. So the best we can estimate is that they are in a fuzzball, if you will. Doesn't sound very precise, but again, then in healthcare, we're not concerned about the fact what the orbitals are like. We're more concerned about how the atoms are going to work in our bodies. Okay. So what do the atoms look like? Well, using our planetary model, here we see the first 3 atoms. Hydrogen with 1 electron and 1 proton. Helium with 2 electrons and 2 protons. Lithium with 3 protons and 3 electrons. Notice that lithium has to have a second orbit here, because there's the nucleus with 3 protons right there. Got to have 3 electrons. Turns out that first orbit can only hold 2 electrons. So we have to have a second orbit out here, a little further away. So because we can get our 3 electrons. Can't put our 3rd electron in this first orbit. Don't know why. That's just a rule of physics, chemistry, mathematics, energy. We don't have a 3rd electron in that first orbit. We can only hold 2. And so we have a proton in 1 proton in hydrogen, 1 electron, 2 protons in helium, 2 electrons, 3 protons in lithium, 3 electrons, right in there. So those are the 3 smallest atoms of all the elements. Now consider this: helium is one of those unique elements that doesn't react with anything. Helium has 2 protons and 2 electrons. There is no space available in the helium atom for it to react with any other substance. Helium is what we call inert. It can't react. You can't get helium dioxide or helium fluoride or magnesium helium or anything like that, because there's no place for any kind of chemical reaction to occur. Helium is non-reactive. So is neon. Neon is unreactive. So, because they're balanced. There's only a handful of atoms that are completely balanced. Helium is one of them. Okay, let me talk about isotopes. I referred to it earlier. Isotopes are a variation on the same element. For example, carbon. The carbon atoms all have the same number of protons. Every carbon atom will have 6 protons. Every carbon atom will have 6 electrons, always. Carbon atoms contain 6 protons. Carbon atoms contain 6 electrons. The neutrons can be different. And if the neutrons are different, then the mass, the weight of the carbon atom can be different. And so you can have carbon-12, which is normal, everyday, garden variety carbon. It's what most of our carbon is. Carbon-12, it has 6 protons, 6 neutrons, 6 electrons. Electrons don't count in the weight. But if you have, if your atomic weight is 12, and if your atomic weight is 12 and you had 6 protons, which is required because carbon has to have 6 protons. If the atomic weight is 12 and you have 6 protons, then you've got to have 6 neutrons. But if your atomic weight is 14 for a carbon atom, it still has 6 protons. Carbon always has 6 protons. If you have carbon-14, that means that the atomic weight is 14. It means that you have 6 protons. You have to have 8 neutrons. Isotopes are unstable. That's the thing about isotopes. We can have variations on the number of neutrons. It's only the neutrons that make the isotope. We can have variations on those on the atom. We can have isotopes of the atom based on the number of neutrons. But the more neutrons you have in an atom that are not, if your weight is different from the average mass, then that atom is unstable. A carbon-14 atom is unstable. A carbon-14 atom wants to become stable, and so it will release energy to kick out the extra neutrons. The neutrons are held in place by energy, and unstable isotopes, unstable atoms that are called isotopes, will kick out energy, and that makes them radioactive. We call them radioisotopes because they're going to decompose down to their stable form. And so an isotope will kick out neutrons and release energy. That's what makes them radioactive. And because they want to become stable. Everything in chemistry, all atoms in chemistry want to be in their most stable form. So they will kick out energy. They will kick out neutrons. They won't kick out electrons or protons because they're balanced. But it's the neutrons that are making them unstable. For example, now here's an isotope. Here's an isotope. Here are isotopes of hydrogen. 3 variations on hydrogen. The first one on the left is normal hydrogen, 1 proton and 1 electron. Deuterium has 1 proton, 1 electron, and a neutron. Its atomic weight is 2. The atomic weight of a regular hydrogen atom is 1 for the proton. But here we see deuterium. 2 has an atomic weight of 2 because it has the proton and the neutron. Over here, next to it, we have tritium. Tritium has an atomic weight of 3. It has 1 proton and 2 neutrons, giving it an atomic weight of 3. If you've ever heard the term heavy water in dealing with nuclear energy, heavy water is made of deuterium hydrogen atoms combined with oxygen, because the deuterium can apparently absorb more neutrons. So that's sort of atomic physics in a nutshell there. The deuterium is what makes heavy water. So anyway, we're not talking about heavy water. The point is, though, that same atom, it's exactly the same atom. They're all 3 hydrogen atoms, but the one in the middle has an atomic weight of 2. The one on the right side has an atomic weight of 3. They're different. They have different properties now because of the neutrons, and they are unstable. They will decompose. They want to decompose down to their stable form. They want to get to their stable form, and they will give off radiation, either alpha particles or beta particles or gamma rays, to release energy to kick out the neutrons. Now, there is a purpose. There is a use for these isotopes. In healthcare, we use radioactive isotopes for testing and for treatment. Since they have the same properties as even though it's an isotope, it still has the same properties of the non-radioactive atom. An isotope will be taken up in the body the same as any other type of atom would be. For example, iodine. Iodine is absolutely essential for the manufacture of thyroid hormone. Our thyroid gland in the middle of our neck manufactures thyroid hormone, which regulates our metabolic activity. How fast do we burn up food? Well, that's controlled by the thyroid hormone. Thyroid hormone won't work without iodine. We get iodine in our diet, usually from salt. We can, if a patient is exhibiting problems with their metabolic activity, for example, or if they have a strange lump in their neck, which might be a tumor, we can measure the activity in the thyroid gland by administering an isotope of iodine. The iodine will always go to the thyroid. If an area of the thyroid is not functioning properly, it won't absorb the iodine. And so what you're seeing here in the illustration, in the microphotograph, is a thyroid gland. It's actually a microphotograph. It's a full-size photograph of the thyroid, because the thyroid's about 3 inches by 2 inches in your neck. It's pretty big. We see a dark area where nothing's working. where the iodine is not being taken up, because that iodine is radioactive and it will glow on, an X-ray. Very simple, non-invasive approach. You don't have to go in and look at it. You can just take this, get this imagery here and say, oh, well, there is growth taking place in there. And a pathologist would say it's benign or it's malignant, it's cancerous or it's harmless. The point is that by using the radioactive iodine, it goes to that part of the body and only to that part of the body. Iodine is only taken up by the thyroid. We can measure the activity of the thyroid gland. If we were to increase the strength of the iodine, we could use that to kill a tumor in the thyroid. We could administer that as a treatment to destroy a thyroid cancer. So we have a lot of uses for radioisotopes in healthcare. It can be used to kill radioactive isotopes can be used to kill cancer cells in a variety of locations. I mean, if you hear about proton therapy and the proton beam and the proton knife, stuff like that, is simply a variation on using radiation. And these isotopes are one way to do that. So there is a purpose here, for isotopes. The radioactive isotopes that are administered to a patient for a test are very low level, and they break down within 24 hours. You're only radioactive. That's what you say. You only glow in the dark for about a day, but you will be radioactive for about 24 to 48 hours after this kind of test. So it's a harmless test to detect, or problems with the thyroid gland, for example. So again, it has to do, isotopes, if they're unstable, will degrade because they want to degrade down to their stable form. Radioactive iodine wants to get to its stable form. Carbon-14, radioactive carbon, wants to get to its stable form, and it will kick out energy to do that. Energy, and we can measure that energy. Okay. Now, so we got atoms, and we have protons, neutrons, and electrons. What happens with the atoms is atoms don't like to be unstable. And so how is an atom unstable? Well, because it's a pure substance. Well, an atom, as I said, has these orbits filled with electrons, except it only put, if it has, like lithium, had 2 electrons in its first orbit around its nucleus. Remember the picture? Let me get back there real quick. There's lithium on the right-hand side. Lithium has the nucleus in red and yellow. I don't think it's red and yellow for real. And electrons are in orbit around the nucleus. You have 2 electrons in its first orbit and 1 electron in its second orbit. Well, it turns out that the second orbit can hold up to 8 electrons. And atoms really want to have those orbits filled up. An atom wants to have 8 electrons in its second orbit. If it has a second orbital, or a second shell, as we like to say, if it has a second shell with 1 electron in there, it wants to fill up. So it has 8 electrons in that shell. And that drives atoms to combine with other atoms to make molecules. Atoms will generally combine. It is rare to see atoms isolated. Pure elements are hard to find, naturally occurring. Gold, for example, is a pure element. Silver is a pure element. Many times those pure elements that are found in nature are often have to be extracted from other elements around them. But anyway, a molecule, 2 or more atoms bonded together, water molecule, hydrogen and oxygen. A sugar molecule, carbon, hydrogen, and oxygen. So that's 3 atoms. So a molecule, 2 or more atoms bonded together. A compound is generally 2 different kinds of atoms bonded together. Now, technically, a molecule has only the same type of atoms, like nitrogen has, a nitrogen molecule has 3 nitrogen atoms together. Compounds would be different. Compounds would be water, like oxygen and hydrogen. But we just all tend to say a molecule of water, a molecule of sugar. We sort of tend to, push the compound off to the side. It's a whole lot easier just to say a molecule. Molecule of glucose, molecule of nitrogen, a molecule of water, instead of saying, well, that's a compound, not a molecule. So, okay. So if you combine atoms, you can make mixtures. If you combine atoms, you can make mixtures. And matter is nothing, it's made up of mixtures. We have physically intermixed matter. We have physically intermixed matter. Now, this is different from what atoms do when they're combined. When we talk about atoms like to be together in molecules, that's great. They do. Water, hydrogen, and oxygen love to be together. Glucose, all the carbons and hydrogens and oxygens love to be together. We like, atoms are happy if they could be happy. Atoms are happy when they're combined into molecules. And that is a chemical change in here. When hydrogen and oxygen come together, we make water. And that has properties different than the hydrogen atoms and the oxygen atoms, completely different. That's a chemical change. Mixtures, when mixtures occur, it's a physical change. It doesn't have to be a chemical change. Now, a mixture falls into 3 categories. Solutions, which we're all familiar with, colloids, which we are familiar with, but probably not even knowing about it, and of course, suspensions. Blood is a suspension. Let me explain some of this. A solution is a mixture of particles. It's a mixture of particles evenly distributed. What does that mean? Well, consider the room you're sitting in and the air you're breathing right now. You're breathing a solution. You have a mixture of hydrogen and oxygen and nitrogen and carbon dioxide and a bunch of trace gases all mixed together. It is homogeneous, meaning it all looks the same. The air that you're breathing doesn't look different. Oh, look, here comes a nitrogen atom. I better duck that. No, we don't see it. We just breathe. Well, considering that air is 80% nitrogen, you're probably breathing a lot of nitrogen atoms. The point is that the particles are distributed evenly throughout your room. You can't, oh, I better go over to the corner. I have more oxygen over in the corner. I better stay away from that corner because there's more carbon dioxide over there. We don't know that. All we know is that the air we're breathing all looks the same. It all smells the same. It all tastes the same. Solutions are homogeneous and they are transparent. Usually a solution has a solvent and a solute. And even though I'm using atmospheric air as an example, it still works. The solvent is the substance present in the greatest amount. So if we're going to make a solution of I don't know, sugar water, we use water. So we're going to we're going to make sugar water. We're going to make sweet tea. And so we start out with water. Water is the solvent. The solvent is the dissolving medium. Water dissolves sugar. Water dissolves salt. Atmospheric air contains all the ingredients of nitrogen and oxygen, hydrogen and methane and carbon dioxide and all the other stuff. So a solvent is the dissolving medium. When we're dealing with liquids, which are very easy, and since our body is dealing with solutions all the time, both internally and externally, we're going to look at water. Water is considered the universal solvent. It dissolves everything. What is dissolved into the solvent is the solute. If you're going to make salt water, you're going to dump a couple of tablespoons of salt into water, and the salt goes into the solution. The salt disappears in the water. You put sugar in water, stir it up a little bit, the sugar disappears. Sugar's still there, the salt's still there, but it's not visible anymore. The solute is dissolved in the solvent. If oxygen is the solute in atmospheric air is the solvent. If you're going to make iced tea, sweet tea, you're going to use the solvent will be the water, the solute will be the sugar, and the tea bags, of course. So in our bodies, our blood sugar, consider our blood sugar, glucose, which is the simple sugar that makes up our blood sugar. Blood sugar is the solute. Plasma, the fluid part of our blood, is the solvent. So we deal with solutions all the time. Our plasma is salty. We have sodium and chloride. We have sodium chloride, just like table salt, in our plasma. The sodium and the chlorine are the solutes inside the watery solvent, which makes our water, our blood plasma, salty. So solutions are always transparent. You always have a solvent that's dissolving a solute. We dissolve the solute. The solute is the substance being dissolved. The solvent is the dissolving medium. You add sugar to water, you add salt to water, you add oxygen to air. In our body, we have solutions of all types. We have solutions of salt water and sugar water and all these other things in our blood, in our interstitial fluid, in our lymphatic fluid, in the fluid around our brain and our spinal cord. All these are solutions. So we pay a lot of attention to solutions. The concentration of the solution is very specific. 0.09% sodium chloride is the concentration of plasma. We like to stay right in that range. Our blood sugar, we don't like to get above 100 milligrams of sugar per deciliter of water. So our magic number for blood sugar is 100. We like to keep it below 100. So a solute and solvent make solutions, and solutions are always transparent. When you dump sodium chloride into water, it disappears. It's still there. It's not visible. You have a transparent solution. Now, when we're dealing with solutions, and if you've ever had an IV line running into you, or you've ever seen anybody with an IV line, it might say normal saline on the IV bag. It may say 0.9% sodium chloride or whatever on the bag. That's the concentration of the solution. Now, there's three ways of looking at solutions. The percent of the solute is the simplest, and it's the kind used most frequently in healthcare. Essentially, how many parts of a solute are in 100 parts of water? Well, if it's 10 parts salt, 90 parts water, it's 10% salt solution. So the way we would make that is, if you take a liter of water is 1,000 milliliters. If you take 100 grams of salt, sodium chloride, and dump it into a beaker filled with a liter of water, well, the 100 grams of salt is equivalent to the 100 grams of salt in a liter of water is a 10% solution. 10 parts salt to 900 parts water, 10%. When we make solutions up in the lab, we would make up, if you want a 40% glucose solution, 400 grams of glucose into a liter of water, or 40 grams into 100 milliliters of water. That gives you a 40% solution. If you want a 10% solution, a 20% solution, the 0.9% solution, 0.9% sodium chloride is 9 grams of salt in a liter of water. I think that's right. I'm not sure in math, I think it's right. And so we make up a concentration that is equivalent to what's in the body. This is the most common way we measure solutions. Milligrams per deciliter. I mentioned that earlier about a deciliter. A deciliter is 1/100th of a liter. And we tend to use that only when we're dealing with blood sugar levels in the body, like anything below 100 milligrams per deciliter is what we're not going to make up solutions with deciliters. We're going to measure in deciliters. So when you get blood sugar level results back from the lab on a patient, it's going to be in deciliters. So, okay, I'm going to stop here because I have probably 10:59 or something like that, 10:58. Let me stop here. I hope that this hasn't overwhelmed you as far as the chemistry, because I'm trying to put it in the perspective of how it affects us, how it affects healthcare. This is not a chemistry class. This is not a course in chemistry. This is not to make you all chemists. This is to show you how we use chemistry in healthcare. So, if anyone have any questions on this, we need to get out of here. So if you have any questions, shoot me an email. This will get posted in YouTube today, and I'll shoot you the link as soon as I have it. Otherwise, I will see you all later on. Thank you for coming today. I appreciate it.